integration by substitution. So any questions about it? So the point is that so the current homework isn't about that. So that you shouldn't take it as you should wait. Probably a good idea to start trying some of these problems early on when it's still fresh. But the next one will be about integration. The next homework next week. So we have a week next, and then we have a break. Okay. Okay. So let's see. So this is the list of integrations right here. It is a very short list, but very similar in nature. In the let's say these three at the top. That is clear reversal of differentiation. So there should be no doubt about where it comes from. This is where it comes from. You differentiate sine x squared, and you have cosine x squared to x. So that's all the chain rule applied every time, and you get that function. So that's why it is not a coincidence that you have always two terms, right there at the top. You have two terms. Why? Because the chain rule produces two terms. And now, if we try to reverse the chain rule, then we got to start with two terms. So the original function that is being differentiated is a composition, and the end result of this differentiation is two functions multiplied by each other. And then if you to reverse it, we have to start with two functions. So if it's not two functions, you're not gonna make any progress. So once again, that question, that ex squared dx, say this is the integration by composition is of no help here. Why? Because there is no second term. This function is not the result of the chain rule. Okay, so that function over here, x squared, is not. Does not come from the chain rule, therefore, well, we cannot apply differentiation integration by composition. Okay, so having said that, there's still a method there in this. There's a logic there that sort of allows you not to try to guess where it came from. I mean, it always comes from the chain rule, but guessing where the exact function it was. Sometimes it's easy, sometimes it's not, and so it's better to have a method that guides you towards the answer, if there is one. Okay, and the method is substitution. Okay, so the chain rule is a substitution. This still is substitution. Okay, so well, in either case, you have to decompose the function. That if there is a composition, it needs to be decomposed, just the way we did over there at the bottom. Square root of x squared plus 1. Well, that is the two functions that will be our parts they are composed. And then, just like with the chain rule, that part is very similar. So still recognizing the compositions, pointing out the parts of the composition. In fact, even in other similarities, you have to differentiate that function on the inside. X squared plus 1 still has to be differentiated in order to proceed. Okay, and so that is the plan. The point is, however, as you can see at the third example, the one that's circled, we did not try to well, maybe we did, but we didn't have to. We didn't have to guess what the answer was, but rather we went through this slightly convoluted process. This is the very last thing we did to find the answer. So let's review this once again. So we have a function. Okay, so we see, first of all, to see is the composition in the yellow circle, which tells us that it is a composition. So it's probably the chain rule. There is no integration by substitution, because there is no other method at this time. So and there isn't. I believe if you see a composition, I think it's invariably substitution. And but sometimes there's choice of what is that your function should be. In this particular case, you pick the natural choice for the decomposition, so u is equal to x squared plus 1, okay, right here. Okay, and then we also notice not only the decomposition, we also notice that second term, 2x over there. So we have two parts, so it is we are on a good track with integration by substitution. We picked substitution equal x squared plus 1. We differentiated, found dy dx is equal to 2x. And then we actually carry out that substitution, why it's called integration by substitution, because we do substitute. Okay, so and two things are being substituted in addition to the variable itself, which is very standard, which is just pure non-calculus like analysis of compositions manner. X squared plus 1, we set it equal to u, and now we replace x squared plus 1 with u. Okay, so that's the first part here, first part of the substitution, and then the second part is what to do about dx. Okay, and that is not, it cannot be left alone. So that is actually, if you look at this one, this is really not a good thing to have. You certainly cannot do anything with it. If you have two variables dependent on each other, u is a function of x, as you can see, and so to integrate it, you have to finish. So let's say, put it this way, finish the substitution. So just doing u is not enough. Now you have to introduce du somehow, and that's how it is introduced. We realize what du is, and it is 2x dx. Okay, so so that's how it works out in terms of substitution. And but as I promised last time, I feel obligated to at least provide something of a, if not a reason why this works. We actually know why it works. It's the reverse chain rule. What I want to provide you with is at least the idea where, well, under what circumstance, in what sense we can treat dx and dy or du as actual numbers rather than parts of one piece of notation. Du dx, one thing, it is the derivative. Okay, so it's not to be taken apart. So under what circumstances du dx or dy dx is a fraction. So as I point out here. So otherwise things have worked out. I just want to quickly point out where it comes from. And it comes from differentials. That's what it's called. Those are differentials. Dx, dy, they're called differentials. So these are there. So even if we took dy dx and broke it into two, we're not going to break these two apart anymore. Okay, they are in fact numbers, or they're not even just numbers. These are variables. These are two variables. So it's like new variables. So in what sense? We start with a function. Okay, so we always initially talk about functions of the derivative of a function at one location. Okay, so this is f of a. Okay, and then where is and then what we do know is that we can write f prime of a is equal to dy dx. That's just two different notation. So same, different notation so far. But we could actually see these dy dx dy as new variables if we just look closer, if we zoom in on the graph and plot the tangent line. So let's plot the tangent line. Well, it passes through the origin, not that it matters. Well, let me take it off. Okay, so so this is the tangent at A. Okay, so this is still y equal f of x, I suppose. Okay, so these are the variables. Okay. So we zoom in on that point. So we have a point of interest, this one. Okay, so and that's what the derivative is. It doesn't matter where things are, where the graph is located. It's slope at that particular point, the shape and the slope that matters. And if we zoom in and then we try to ignore everything else, and then we concentrate on what is the tangent line. So that's what I'm trying to do here. So we have this coordinate system with a line. So there is no function anymore. So we don't have to speak of a tangent line, but this is what this line is. Okay, so there is some point somewhere. It is actually 0, and then what is the line? The slope of the tangent line is f prime of a, right? The slope of the tangent line f prime of a. So if we take the graph of the function that I have here, now this time there is no x and y, but there are dx, dy. There are two variables that reflect what is the meaning of dx and dy. They're just how far we step off that point to the left along the x-axis or to y along the y-axis. So anyway, if I take the slope is equal to f prime of a, then and then eliminate what I move the whole graph to the origin. Okay, and then it means that the slope is all we need. In fact, so let me repeat that. Slope is f prime of a. Which is just a number. Okay, so what is the equation then? Let's find the equation. So equation of a straight line through the origin with the slope f prime of a. What is that equation?
Y equals mx plus b.
Well, almost. So the generally is y equal mx plus b. The only thing that we're going to change, so that's the general situation on the left. So first of all, there's no b because it passes through the origin, firstly. Secondly, what's the slope? We'll look at it, f prime of a, so this is f prime of a. And now also the variables have been renamed. They're different names. This is dy and this is dx.
So dy equals f prime of a dx.
That's right. And these are nothing funny going on here. dy is a number variable, dx is also a number variable, and f prime of a is also a number. So this is what we're looking at is nothing but the equation of this line in this special coordinate system. And then if you want to, you can actually divide by dx, and what do you get? You get this, where we came from. So it's just two definitions of the derivative, or two notations for the same derivative. They just can be written in a different way, and if you pick the correct variables and correct coordinate system rather, then it actually does turn into the equation of a certain line, which is just not certain line, but the tangent line, and then f prime, as we know, is its slope, and then just the variables are chosen carefully. You end up with indeed two numbers, dy and dx, and they are related to each other through this derivative, through this number. So you simply multiply dx by that f prime of a, and you have dy. Okay, so that's in that sense. That's how we can always. That's how we justify this part when this part, that du is equal to x dx. Of course, if now I take what I have here, this analysis, and if it just happens that my f of x is equal to x squared, then I'm going to have then f prime of x is equal to 2x. and then that's what I end up with. I will end up with dy is equal to 2x dx. Okay. The only difference is that I have to carry out this thing, that construction, little construction of zooming in on the point at every, and I have to do it on every for every location on the graph. Okay, so for example, I will have another situation very similar over here. If I pick this point instead of the original one, I will still have dx dy to perpendicular. It's still Cartesian system. Yeah, I could still call them dx dy, and then there's still tangent line there, and this equation still is applicable. Okay, but this one is, as you can see, how it works out for dimension 2. It is a device that the way we have used it here. So that's just an explanation, and it does actually have profound consequences. It is come out big time later on in calculus 3 especially, and beyond. But really, as far as integration by substitution is concerned, the justification for it is nothing but the chain rule. Okay, there's period. Chain rule gives us the formula that I'm about to provide, and this is just a device, a trick, a kind of a trick with notation that allows us to literally convert integral with respect to x to one with respect to u, that new variable. And we're using this relation between x and y. There's a functional relation between them according to the substitution formula, and then we just replace dx with dy. And in that particular case, you don't just say dx is equal to dy. The relation if the relation between x and u is complicated, then the relation between dx and du is also complicated. It is also functional, and how functional? That's how. So in that sense, as I just explained, this is actually truly this term. This over here, it's a very questionable thing that is being asked. It is kind of seems kind of funny. But it is actually multiplication. So we end up multiplying by dx. Another way to see why this makes sense, just go all the way back to Riemann sums, and that is that you will have literal multiplication by delta x, and it's also explains that explains the notation. Even it is kind of funny. Okay, so let me state the formula, and once again, entirely based on the chain rule. Chain rule. Suppose I have two functions, f capital for some reason, as you see in a minute, and g. Okay, and differentiable. Then, by the chain rule, I can differentiate the composition. Okay, so that's the function. Its composition I differentiate, and it will be f prime of g of x times g prime of x. That is the chain rule. Now reverse. Reverse the whole thing and read it backwards. So from differentiation to integration. So if you like, I can go this way: f g of x, arrow, differentiation, f prime of g of x times g prime of x. Okay, and now back integration. And that gives me integration by substitution. So it's also a theorem, but there is now nothing to prove because we already have. So, okay, so once again, two functions. yes, f and g. And then what we have here is, so I'm reading that diagram from right to left, so I have integral f prime g of x times g prime of x dx is equal to f of g of x plus c. Okay, so it looks complicated. It is a discouraging, I guess, thing that with the point where you start is actually more complicated than where you end. Well, that's because we came from the chain rule, and the chain rule it works the exact opposite way. You have the composition, at the end you have a function that's kind of more complicated, but it's worth it because, well, the problem is solved. Unfortunately, it's not as easy with the integration by substitution because it makes things more simpler. You'd think it's good, but really, then when you have a function, we already had faced that. When you have something to integrate, you have to recognize these parts. We already did it, but there's a challenge there. So we do know that if there's a composition, we can detect it. Okay, especially when you see square root, or when with some expression inside, you see parentheses, you have exponent with some expression over there. Those are compositions. We'll know that. So recognize number one, composition, and number two, the derivative of the function on the inside. There is, in other words, there is a derivative. There is a relation between the parts of the formula, the function on the inside, derivative on the outside. Without it, it's not going to work. Okay, so when you recognize these parts, then you will see the formula. But at least there is one way to slightly make our life easier, and that is we'll put it this way. So second version. So just replace f prime capital with f lowercase. Okay, so that way we don't have to start thinking whether this function is derivative or not. So this is what it looks like. Integral f of g of x times g prime of x. So that doesn't change. So it's still kind of complicated. And now in the right hand side is the same. Okay, so but there's an explanation. F is an antiderivative of f lowercase. Okay, so in other words, we don't have to try to deal with f itself in the very beginning. You just point out there is an f there, and we know if we're going to do substitution at some point, we were to find its antiderivative, but at least it will be postponed until later. So until we did all the decomposition, apply the and possibly it would apply the formula. We'll know where we are. If we will be able to finish this computation. In fact, how should I put it? It's kind of a two-step to get from left to right. Then we not only have to decompose, but we also have to find a f capital. Before you find uppercase f, you cannot move from left to right. So you have to actually, this is how you write it, f of x is equal to integral fx dx. That's the definition of antiderivative. So once again, the plan goes this way. So decompose, identify g and g prime, that you should be able to see them. And then, or maybe we have to manipulate things a little bit. So, and then you find f, and then once you found f, then you're done. Then you can just substitute them into the formula. So it is a two-step procedure, and that's the way we did it. If we take a look at this formula again, so identification, and so we did not know ahead of time what to do with f. So that is the function that we, the square root is the function that we originally ignored and didn't try to deal with it right away. Yet we still were able to carry out, well, I guess, hold on a second, I don't think that these arrows are correct. Actually, you finish the computation first. You finish the transition first, and then you find an antiderivative. In fact, let me fix something that might help a lot. The variable isn't x. The variable is u. Not to be confused, right? So that's the nature of the decomposition. We have the substitution is u equal g of x. Okay, so that is the transition that we're facing. Well, let me correct some more. Oh, here it is. Okay, I think that makes the most sense. Okay, here it is. Okay, like this. Okay, so on the right, certainly it looks complicated. Okay, you don't know how to find it. That might be a problem. And then, I'm sorry, this is again, shoot, it's for some reason I'm making this. This is once again is u. Okay, shoot. Okay, that makes more sense. Okay. So once again, how do we do it? We pick the substitution. So that's step number one. Okay, step number one, we pick the substitution. Then we find g prime and deal with it somehow. Okay. And then we identify f. Okay, so that should be clear because we're doing decomposition. And then we carry out the substitution, but not before. Well, and then we carry out the integration. Okay, so this is the last step. So this is 2, and this is 3. Okay, so the actual integration with respect to the new variable is the last step, and well, the step number 4 is back substitution. So back to x. Okay, so once again, let me take a look at what happened here. So here my function f, lowercase, is the square root. Okay, this is my u, or g if you prefer. Okay, the x squared plus 1. Okay, so we pointed out what our new variable is. We found its derivative right here, and then we ended up with, when we carried out all the substitution properly, we ended up with this over here, the integral with respect to u. Integral of this is integral fu du. Okay, that function it is fairly straightforward if everything else works out. Okay, so that's a plan. This looks more like a plan than what we had before, and it is as you can see, it comes from nothing but. So this is version 1, and this is version 2. It comes from the formula for well, in 2 steps, but we start with the chain rule, reverse it, we get the original formula, which is the one in purple. It is kind of cumbersome, so hard to use. As a procedure. The version 2 is more like a procedure, but probably we could do a better job, and probably I'll do it later. But let's carry out a few examples of this before we try to sort of formalize the procedure. So okay, so once again, we're not trying to integrate too early. So this step is delayed. We don't try to guess what f capital is. So for example, we need to evaluate, say, okay, how about this one? E cosine x, sine x, dx. It looks complicated. So it looks complicated, so what are the good news? The what?
The cosine and sine parts are easy to derive.
To derive? Yeah, so the good news is that all the functions that are involved are familiar. So sine, cosine, exponential function, we know all their derivatives and antiderivatives. But what I was talking about is there is good news in terms of the applicability of the integration by substitution, and there are two. First of all, you see a composition. Okay, composition. If there is no composition, it's probably not about the substitution. And secondly, there are two terms. Two terms to integrate. Function is made of two terms, so it may have come from the chain rule. So that function e cosine x sine x may have come from the chain rule. Okay, so that's the good news. But we don't want to guess and take that idea of good news all the way through. Let's just let's follow the procedure. So once we identify the composition, let's point out what those functions are. So look at it. We have to, well, what is u? Step number one. Rule of thumb, pick the function on the inside for the new variable. Cosine x, yes, cosine x. Okay. So then what is f of u? We are still looking at the very first term of our function. E to the u, yes. Okay, so that is almost the whole thing. I mean, the premise is here, so that's the starting point. So we'll find out quickly whether it works or not by starting with the substitutions. And so these are the two assumptions. We identify u and we identify f. Okay, that's enough. We are going to need the derivative of the first and antiderivative of the second. So we have du dx, that's easy. It's negative sine x. Okay, and let's just plan ahead. Let's integrate this. Fu du is equal to eu plus c. Okay, so we might never need the second one if it doesn't work out, but maybe we will. Okay, so the point is that we are ready to differentiate one function and integrate the other function, and so we do it just in case. Now let's carry out the substitution. So that's the step 2. Step 3 into do its substitution. So our integral is e cosine x sine x dx, and just plug in things in. So I have integral e to the u, right? So cosine x. The sine x, I cannot do anything with sine x. I could, but I don't, certainly would be a mistake to try to express sine x in terms of cosine x and finish that substitution, because, well, why is it a bad idea? Because even if you carry that out, and we could do Pythagorean theorem and express sine in terms of cosine, and we could finish this substitution, but then you still have dx. What do you do with dx anyway, right? So that part remains unclear. So in fact, let me just write, spread it out a little bit. So we did one part of the substitution. The second part is this one. We literally do the substitution. So we need to replace dx with something, and where that something come from over here. So dx, let me write it here. Dx is du over negative sine x. That is what I'm going to be substituting. Okay, so if I substitute, I have e to the u sine x du over negative sine x, and things cancel out. Okay, so by design, not by design, even though not by our design, but by design of the problem, of the person who designed the problem. Okay, so that's the design. Okay, so we end up with eu du with negative sign on the outside, which we already have integrated right there. And so we know the answer. It's negative eu plus c. Step 3. Step 4, back substitution, and we're done. So it will be negative e cosine x plus c. Always a good idea to confirm the answer and just watch how that second term appears. So let me add one extra step here, verification. So I take negative e cosine x plus c. differentiate. Inevitably, I'm gonna apply the chain rule. Negative sign is not a big deal. C is gone, and I differentiate e cosine x with the same, by the way, with the same decomposition. So that decomposition can be recycled, the decomposition being this one, can be recycled for differentiation. And so in the derivative already is known, it is negative sine x, right? So I will have e cosine x. The derivative of EU is EU, and times sine x, negative sine x. So we end up e cosine x. Okay, so it confirms sine x. I'm sorry, sine x. The answer is confirmed. Everything is fine. That's you recognize in retrospect. In retrospect, you recognize where things came from. The relation between these two is that one is the derivative of the other, and so once again that's how it works out. And it's so you realize again that this is all about the chain rule. Okay, so the technique is fairly straightforward, and but it becomes kind of art at some point, not in this course but in calculus 2, and that is the art is finding which substitution to carry out, so which one to pick. I'm not a big fan of mathematics as art. Because it's art means it turns into trial and error. So you try this and try that, and hopefully you find it. I mean, the one is just as an example, 1 over 1 minus x squared. What should be the substitution? So it is impossible to guess. And there isn't even a composition there. And the answer is it is trigonometric. What makes it trigonometric if you think about it? And on the surface you cannot see, but that's actually the substitution that works. Okay, so that's all have to wait until calculus 2. So in this course we pick primarily very straightforward. Then in this substitution, that is the one that you would guess if you just look at it. If you understand compositions, you'll see the two functions. You'll see one on the inside. That is always the one that is to be chosen as your new variable, and you just carry out according to this little plan. Okay, so but you have to see that how well it is located within the course. This method, because it brings together all these things, the chain rule as well as integration, as well as differentiation, as well as just integration of straightforward things. So that's just a lot of stuff throughout that came from the rest of the course. Okay, so let me see if I want to take maybe another example of this. So the point here is there was a subtle point here that I skipped, but I think you should see it, that that negative sign was a little bit of a discovery. We were not able to, by just looking. Remember, the derivative of cosine is not sine. So we were kind of confused about. We would not have guessed possibly that it is indeed came from the chain rule. But if we carried out the plan, then it kind of falls into our lap, because, well, that negative sign just appears over there, and it is just a cancellation. The same way, if you try to integrate, say, as we have previously, say cosine x squared 2x dx. All we did, we recognized that this is the chain rule. Came from the chain rule, and the answer is sine x squared plus c. Okay. What if, however, we had cosine x squared times x dx? Okay. So that disappearance of the two creates a little bit of a problem. It makes it impossible or less likely to be able to guess this function. So once again, that's what we did a while ago. So we guessed the answer for cosine x squared 2x. If there is no that 2, then the derivative of x squared is not visible anymore. So that might be might be a problem. But with the method of integration by substitution, it's not a problem whatsoever. That extra 2 will appear in a natural when the time comes. So say du dx is simply 2x, and then dx is equal to du over 2x. So that's where that 2 comes from. And then so the answer is what is it? 1/2 sine x squared plus c. Okay. So with practice, you will it kind of works out fairly easily, in the sense that the steps are the same every time. It's just many moving parts, and so there's good chance that you might make a mistake, and then so that might mess things up. So I want you to also to see that just in case, the formula, which formula? This formula, I suppose, and they compare it to the linear formula for the linear substitution. Okay, so once again, notice that we integrate our function f, and now imagine for a moment that our function g is linear. If g is equal to g of x is equal to mx plus b, then g prime is simply m. So there is nothing to do but nothing. It does not add anything. This one does not add anything but a number. Okay, so then you don't really need a formula for that. If you do linear substitution, that's frequently when it's a composition of a function with a linear function. All you have to do is just to you almost guess the answer, but you don't have to. Okay, so over time we'll do more of this. Well, one topic that fits right with this is what happens to the definite integral, to Riemann integral. So with the one with limits. So we're computing areas, and then what happens to our integral. One way certainly, so let's look at this problem, and suppose I am interested in integration from, let me just correct it slightly to make that point so I don't have to write it from scratch. So suppose I'm looking at this graph, this function, there is a graph, I don't even know what it is, and suppose I'm integrating from, say, 0 to pi. Okay, hypothetically. So what do I do then? Well, if you remember, so we know an antiderivative of this function, and now I'm supposed to evaluate the definite integral from 0 to pi. How do I find it? So this is antiderivative. How do we use antiderivatives to find definite integrals in the areas and the graphs? Equation of the area on the graph. So what's the formula for the area on the graph? Either you remember the formula or remember the name of the formula. Anybody remembers the name of the formula? What? Well, the Riemann, no. The Riemann sum gives you the integral. So this is, if with the pi's, with the limits, this is the Riemann integral. which is the limit of the Riemann sums. Okay, so that is not the way we want to compute it. This is the Riemann sum was used to define it, to explain it, and then we had a certain formula or a theorem that allows us to compute the Riemann integral without referring to Riemann sums. What was it? It is the fundamental theorem. Fundamental theorem of calculus allows you to indeed compute, this is the formula, you should remember, f of b minus f of a, where f is an antiderivative. Okay, so once again, the ability to find antiderivative, which what was this problem, the discussion has been about, allows one to avoid Riemann sums and limits and just plug in the two values. So have antiderivative, then plug in two values. So then we have it. We have that f capital. Suppose so. What I'm talking about, this is f. This is f. Okay, what we're integrating, and then f capital is at the end. This one, what we found. And then, so then our integral is our integral with limits. So say 0 pi fx dx is negative e cosine pi minus negative e cosine 0. Okay, c is thrown out because it cancels anyway. But that's the fundamental theorem applies. And so once again, knowing the antiderivative allows one to eliminate altogether everything from all business and trouble with the Riemann sums, and just it really becomes a very simple computation. Okay, so in fact I could easily finish it. Cosine of pi is negative 1, so 1, 2. So see how easy it is. So how the antiderivative of how much information it contains. So it gives us the answer for free. Now, but that's not really the point. The point is every time if you can anti-differentiate and whatever the chain, the integration by substitution or any other way, then you can find areas. You can find areas. So in areas, remember, they might mean a lot of different things, including weight or distance, displacement, distance covered, displacement, and so on. So we for the sake of this method, we ignored all the applications and concentrated on these steps. But really, it is very applicable is if we can handle those antiderivatives. The point is, however, is the limits. There's a little bit of waste here because we actually can carry out the fundamental theorem at the end without doing back substitution. We could carry out the fundamental theorem with the new variable. So what I'm talking about is this is x. Okay, and that's what the fundamental theorem is. But on the other hand, we really don't care how we compute the area as long as it is computed. So we could just as well do the that with respect to u. Okay, so then this is where we would have to step in with the limits. So ignoring this, not doing back substitution. It's no big deal, but it is actually important to understand that we don't have to go all the way, do back substitution, find antiderivative, and keep going, while we already have a new variable which is just as good as the original. The only thing that's missing is just to figure out what the limit's supposed to be, but with that's all. And then carry out the same thing with a simpler function. We should appreciate that with a new variable. So what are the limits? The limits are, so what are the limits? X is equal to pi. What is u? What is u? Well, look at it's circled on the left. The relation between u and x. So cosine pi, which is -1. Okay, and then we do the same. X equals 0. U is equal to 1. Okay, so these are the limits for u. So the way then I could proceed is, in fact, like this. Negative integral. No, I don't need integral anymore. I'd rather, well, in fact, the arrow should point here. I don't need to integrate. I mean, I have integrated. So at this point, what I do is negative EU with limits u from 1, rather from 1, yes, to u equal -1. Okay, and then we end up with 2 again. I think it's -2 actually. Well, so that's just an explanation of it. I tried to just put it on top of the problem we just solved, but there is a point there, and I'll do one more example of this. So when we need to compute the area actually, rather than just an antiderivative. In fact, probably this is where I can have a formula. So let me point out what the formula would look like. Not here, but so this is our integration by substitution formula. Here it is. So we will jump from the integral for x on left to this one. We'll jump to this one. The only thing, there will be limits, but they will be different. The original limits are with respect to x. The new limits will be with respect to y. U. Okay, so let me write that up. Okay, so integral from a to b f gx g prime of x dx is equal to integral fu du. The only thing that remains is the limits, so where they come from, but it is totally determined by our substitution. So with substitution u equal g of x, okay, so we do just what we just did. So this is version 3, sort of the integration by substitution formula. So what are the limits? The limits correspond. Let me actually, this helps a lot to avoid the confusion. So there is no doubt that the first integral is not only the functions are with respect to x, the limits are also with respect to x. New functions, not only the function is with respect to u, the limits are also with respect to u. So all you have to just to see is how we get from a to what? What's the corresponding limit for u? You just substitute, right? So what's the lower limit for the second integral? mean G of A. I think that's what you're saying. G of A. Okay, and this one is G of B then. So that's what U does. If you just think about every single thing on the in here, then G of X is replaced with U. But on the end, that's what we did. You can see it. G prime X dx is replaced with du. So every single part. Let me just circle the things that have been replaced. So G of X is replaced with U. Okay. G prime of X dx is replaced with du. Okay. And the limits are replaced as well. So x equal b becomes G of b, and finally, I'm out of colors. This one. X equal a under G becomes G of A, right? So sometimes things becomes more simple. I would not insist on doing, if you were doing it necessarily through this formula. It's a nice formula, but there is nothing. It's not necessarily a particular simplification in comparison to the procedure that we have had. There are always two ways. Either you carry out the substitution, do back substitution, come back, have your antiderivative for with respect to x, then do the limits. Okay, there is nothing wrong with that, and it's now worse or even harder than this method, which is convert to u once and do the limits with the new variable. Okay, it doesn't matter. So let me just give you a little bit of an example. So what is the substitution? How about sine e to the x dx? Okay, you certainly can guess what the answer is, and then suppose you need to do it from 0 to 1. Okay, so you can guess the answer, but let's apply the method anyway. We identify our new variable u. U is equal to e to the x. You compute right away du dx as e to the x. Okay, and you will know that in fact dx is equal to dx is equal to du over ex. Okay. Secondly, what secondly? Well, let's substitute. Let's just substitute, and what we have then is equal to integral. I still put x's here, just so there would be no confusion. I will just do it one step at a time. So it will be sine of u, and then e to the x, and dx I substitute is du over e to the x. So e to the x cancels. That's good. But then I'm still left with integral, and then now I'm not confused about the limits. They're still x. So I'm copying, and I have sine u du. Okay, so I could keep going if I want to. I could actually finish the integration, and I'll have integral of sine is negative cosine u. X from 0 to x equal 1. Time has come to substitute, and I cannot substitute because my function is of u, and I have x's here. Okay, so I have to do something about that. What do? I do what I just did. I replace the limits with respect to x with 1 with respect to u. So when x is equal to 0, with this being our substitution, x is equal to 0, what do we get? 1. And x equal 1, u is equal e. Okay, so we have then negative cosine e minus negative cosine 1, or whatever that is, negative cosine e plus cosine 1. Okay, so as you can see, it's was it of any savings? Does it really save us a lot of time in comparison to the kind of standard way? And the standard way would be to ignore the limits altogether and just proceed once you've found that I'm sorry, this is u over here. And proceed from this point on. Well, let me just do that. This is where sort of they fork. So I could fork over here and go back and do it. So I mark here, see the job is done, this is the answer. But I could split here and do it in a slightly different way. So I do back substitution instead. So it will be equal to negative cosine of e to the x. Okay? And x run from 0 to x run to 1. What's the difference really? I mean, it works out exactly the same way. It's just good thing to know that so x equals 1 minus cosine e x equals 0. Okay, so certainly the answer is the same. Okay, so very little twist at the very end, and it looks like the different. Sometimes it might be beneficial, but I wouldn't worry about or give it a lot of thought. It's really not worth it. The formula is worth it, though. It has some implications, even though I can't recall right now a good example for that. But like I said, if you think that you just do integration, so in other words, even though the integral is definite, what you could do is just drop the limits altogether first and find antiderivative. Work the way all the way through, and then at the end apply the fundamental theorem. Okay, and then that's fine. Okay, so let me see. I think we are okay on time. So Thursday will be busy, but until then, there are a couple of topics that we're gonna discuss, more applicable applied type. Okay, so I guess I have run out of things to say today.